Microphone.
Yep, here's the second microphone.
This one.
Okay, everybody, we're about to start the next presentation. So if you could all take your seats, and I hand over to Christian and Simon.
Yeah, so hi everyone. Welcome to our talk, Introduction to Eclipse iceoryx. This is Christian, I'm Simon. We are from Bosch, and about 2 years ago we started the internal development of Eclipse iceoryx. At the end of last year, we open sourced it. Let's have a brief look at the agenda. Our talk is split into 2 parts. So first off, we were talking about Eclipse iceoryx, and then the second part is a demo of the robot Larry, and you got the ability to see iceoryx in the wild. And it's a spare time project. It's not associated with Bosch. Eclipse iceoryx, I'm going to briefly talk about the motivation behind it, then show you how a typical middleware nowadays works like, then discuss how Eclipse iceoryx is doing things differently, and briefly discuss also some lessons learned. So first off, why does IPC matter? Well, this is why. Autonomous driving is very complex. And with autonomous driving, you're dealing with a data-driven system. So different sensors, like a LiDAR and a video camera, are producing data and sending this data to algorithms, and then further to the actuators, for example, a steering wheel. So with the troubles. Yeah, is it fine for you, I guess? Okay. And typically on the systems, you have an operating system. So each application runs in a virtual address space, and you need to overcome this virtual address space. And this is why you need inter-process communication. And the main 2 requirements when it comes to autonomous driving is that we are transmitting large data sets, so up to 10 gigabytes per second. And additionally, we need low latency because we're dealing with a real-time system. So how does a typical middleware like the one used today in ROS work? I'll briefly introduce you to an example. So we have here a publisher, a radar app, sending data to 2 subscribers, 2 algorithmic apps. And a typical middleware, after the data was being written, the data package, copies it to an internal buffers, and then does further copies, like for every subscriber. And if you plot this now, you get something similar like this. So with the increased message size, you get also an increased latency. Now imagine you're sending a 4K video stream. You really have a problem. And this is where Eclipse iceoryx comes in. So I'll run the same example now with Eclipse iceoryx. And first off, what's different? They have to register, all the apps have to register with our daemon called Rowdy. And after they have registered, the communication runs completely independent from Rowdy. So in the second part, the apps map a shared memory segment. This is the red box that you can see here. And inside this shared memory, we have so-called memory pools. You can think of them as wagons. And at the beginning, the publisher requests ownership of such a wagon from the middleware. Then in the second step, the data package is being written into this wagon. And in the third step, we deliver this pointer to the subscribers. And this is what we call true zero copy, because data is only written once and never copied. So now we press the fast forward button a bit. 2 more data packages were produced, and the data package in the beef wagon was already consumed. And here we have a mechanism using reference counting to automatically recycle the unused memory chunks. Now if you plot this again, you get something similar like this. So now the latency is independent from the message size. You get virtually limitless data transmission at constant time. And now I'm going to further dig a bit more into the details of iceoryx. It comes under an Apache 2 license. It's written in C++11. However, we're planning to move to C++14 soon. It runs both on Linux and QNX. In order to establish this communication over shared memory, we're using state-of-the-art log-free algorithms, and we would advise anyone to not directly use this API, but use it with a higher level API. So for example, we offer bindings for ROS2 and also continental integrated iceoryx in their ecal middleware to make it faster. It also can be used as an implementation for the adaptive AUTOSAR communications API, which is widely used in the automotive industry. So next, I'm going to talk a bit about the lessons learned. So up front, we strive for the highest automotive safety standard. Just to be clear here, we are not there yet. Yeah, things are work in progress. But one of the main goals, or the main lessons learned that we learned over the years is determinism is the key. This is why we're not using heap, but static memory pools. So if you configure your memory right up front, you will never run into out-of-memory errors. And also, we are only using a subset of the STL, the C++ standard template library. So we don't allow undefined behavior, and you also get no exceptions. Another very important lessons learned is that log-free programming is really hard. It took us about 2 years to get our main safely overflowing FIFO right. If we would ask ourselves, what would we do different if we would start from the scratch? We would definitely start with the basic building blocks, because nowadays many components are still not optimized, not feature complete. And also we believe that transparency builds trust, and this is especially true in the safety field. And this is why we want to continue the development together with the community in the open. So briefly some words about the upcoming features. We are planning to integrate N-to-1 communication. This is, for example, necessary for the ROS2 logger because many different applications, many different publishers are sending data to one topic. And then also we're planning request-response communication and various language bindings. The Rust language binding is already available. You can check it out. You find the link at the end. Also, we're partnering up with Eclipse Cyclone DDS. This is a middleware, like Jose showed earlier, currently used inside ROS2. And for full ROS2 compatibility, we're also planning Windows and macOS support. So, if you have further questions, you can write to our mailing list or just check out the code. And without further ado, I would give this to Christian.
Thank you, Simon. Okay, whenever I start a presentation like this one, I try to figure out what my main goal is I want to transmit to the audience, and I came up with this here. Is it powered by iceoryx? And the reason here is, if you look at a typical middleware, it does a lot of copies. You have a sender which has to produce data. It wants to transmit this data to a multitude of receivers, and there are a lot of copies involved. Now think of a 4K camera which runs at 60 frames per second. You have a lot of data here, and then performance becomes really a bottleneck. But in iceoryx, we do it a little bit differently. You can say, like, you're sending not data, you just point, there's the data. Take a look at it. And this is much faster. And the second thing is a personal thing. When I started working on this project, I thought it's pretty cool to have something which will be running in a car soon to work on a robot, for instance, in my spare time. And that was started the Larry project. So, who is Larry? This is Larry. Larry is our blue friend here, which is a robot which has a camera up front, which can be rotated vertically and horizontally. You have an ultrasonic sensor. You have also a tracking sensor in front of it, but it's broken, where you can win robo races, for instance. Then we have some LEDs and a beeper on it, and in the future I will plan to pull a microphone array on it and put on some speakers so that I have speech recognition, voice control, and so on, and maybe a 3D stereo camera where you can put on some VR goggles and can become Larry and can drive through a room and with your VR goggles. And I think this is pretty crazy cool. And everything is also again under the Apache 2 license. And now the question comes: can you build your own Larry? Yes, you can. You can buy this whole kit. I think it's 130 euros. The link is here in the GitLab repository. It's not from Bosch, it's from a robo company. And where everything comes together is a Larry Robotics repository where you can find some tutorials how to handle your Raspberry Pi with an Arch Linux image. We decided for Arch Linux, not Raspbian. How to have you get your Larry services running. The Larry services are the applications which are running on Larry, which control the ultrasonic sensor, the camera, the driving, and so on. Then you maybe want to remote control your Larry, and therefore we have a Larry user interface. It's called Larry UI, and there you can log in onto your laptop to Larry and can control him, can make him blink, and so on. And we have some basic applications which, like an emergency brake and so on. And the other thing is, one of my other projects is a spare time 3D engine. You should never build your own, but it makes fun, so I build my own. And if you want to help, you can also get involved here. So now let's take a deep look into iceoryx, how it's really working. I think the best thing to realize how iceoryx is working is by examples, like with a new language, you have to speak it. And here we have Larry. He's inside a labyrinth, and we have to help Larry to find out. It's a very easy labyrinth, and these rules apply only for this labyrinth, but just for the sake of argument, we stick to these rules. The first rule is, if there's no obstacle ahead, drive forward. If there's an obstacle ahead, turn right. And with this algorithm, he can find off this very simplistic labyrinth. Now let's take a look at the code, how it would look like in C++. Before we start with the how the code is ordered. Simon mentioned how we interact with the sensors, algorithms, and actuators. And in this case, we have an ultrasonic sensor which detects the obstacles, though we can realize we are in front of a wall. Then we need an algorithm. In this case, we have an algorithm. These are the two rules to get out of a labyrinth. And then we have our actuator. This is another application which just drives. It receives commands, drive forward, turn right, and so on. And now let's take a look at the algorithm. In C++, this is the whole algorithm. You do not need any more stuff. And with this, we have a very basic application written where Larry can find out of a labyrinth. But now let's go step by step through the code. The first thing is, as Simon mentioned, we have to register at Rowdy. This is the first line. We just say, hello Rowdy, here I am, my name is Explorer. The second thing is we are interested in the data from the ultrasonic sensor, and therefore we have to subscribe to him. And every sensor and every sender has a unique ID. In this case, it's Larry, ultrasonic sensor, intern. When we've done this, we have to create a driver class. It's a very simplistic class provided with Larry services, which does the action for us like driving forward, turn right, turn left, stop, and so on. And we have to define when we are in front of a wall, the minimum distance. In this case, 0.3 meters. And now we come to the event loop. This event loop runs as long as Larry is stuck into the labyrinth. At first, we have to get our sensor data from the ultrasonic sensor. We do it in line 6. And now let's take our X-ray googles and let's take a look what really happens inside. Here we're asking, hey, is there some kind of package we are interested in? And then Rowdy says, yes, there's data. Look over there. We do not do any copy. We just take a look over there and say, oh, okay. There's some sensor data. The minimum distance, for instance, is greater than the sensor distance, the actual sensor distance. Therefore, we have to turn right. Or we do the other thing. Oh, there's no sensor data because the ultrasonic sensor does not detect anything. Or the sensor data detects something, but it's further away than we require for turning right, and therefore we drive forward. And if we take a look at the driving forward and take our X-ray googles again, we're just asking Rowdy, hey, I want to send some data package, give me some memory. And the Rowdy comes, gives us some memory, then we write our memory inside of it, and then we just say, Rowdy, this is the stuff I want to publish, and give it to Rowdy. And then the application which is interested in, this is a driver application, tells Rowdy, hey, I'm interested in driving information, is there something new? And then Rowdy again tells him, yes, there is something new, just take a look over there, no copy involved, and then interpret your data, and this means, for instance, driving forward. So, and now let's take a look at the high-level architecture. It's very simplistic. We have Larry here, our blue friend, and he essentially runs on a Raspberry Pi 4, which does this basic data like collect some sensor data, has to do some pre-processing. For instance, if you have an ultrasonic sensor, you just send a ping out of it, then you will receive some microseconds later the echo from this, and then you have to calculate your distance from it. And this is done also on the Raspberry Pi and not transmitted to a computer, the high-performance computer here. And also some low-level control, like when Larry is driving against the wall, you have to stop him. and therefore this is also done on the Raspberry Pi locally. But the high-performance computer should do perform a high strategy. Let's think you have a swarm of Larrys or like a swarm of Turtlebots, like the previous presentation. You maybe have a strategy like, for instance, Simon is hiding and you want to find Simon. And then all the Larrys can swarm out and have some object detection and try to find Simon. And if they found him, they scream or blink or whatever. So, and here are some ideas which I came up with we could realize together. So if you like them or want to get involved, just write me an email. The first thing I spoke of was a microphone array with speech recognition or voice output. Also, I'm programming a virtual Larry environment where he can train the data with neural networks. Or a stereo camera where you can do 3D reconstruction. For instance, Larry is now a drone and flies through a valley, and then you can map the valley and can put on your VR goggles and take a look at the valley. Or object detection is needed to find Simon. You have multiple Larrys in a swarm. It's also, I think in China they use drones for the agriculture field, and maybe this is also an idea we can follow up, or win a robo race, because we have a tracking sensor for a robo race, so why not use it? And now here the question could come up, if you're familiar with ROS, will iceoryx become the next ROS? And here the answer is definitely not. If you have seen in the previous presentation, ROS has some awesome tools, and we do not need to reinvent the wheel, but we have to help the ROS2 community become even faster. Here we have the problem with the copies and the performance bottleneck, and another problem. Let's say you are a developer and you're developing your cool robot and you want to drive with him through a warehouse, then you have to fulfill some safety restriction. You have to stop when a person comes and so on. And then normally in the old days, you have to rewrite everything from scratch. You have proven that it works, but now you have to redo all the stuff. And here the idea is you do not have to redo all the stuff. We are becoming ASLD, and with this, we can help you to fulfill your security and safety requirements. So, to come with the opening question, is it powered by iceoryx? The first thing is if you have some kind of rover or some other ROS2 project or your own other spare time project where you connected a multitude of sensors and you have a real problem with the performance, just consider switching to iceoryx. We are pretty fast, and we strive to be the fastest in the open source world, and we are at the moment at a pretty good pace to realize our dream. So, are there any questions, or would you like to see a demonstration of Larry?
One question. Question, sure.
Huh?
Microphone. Hang on a second. No worries. There you go.
So if you go back to slide 22, that looked like Larry had to poll a shared memory region to get notified about like there's data available. Is that right? Slide 22. 3. There we go.
Yep.
Yeah. So Larry has to inquire the shared memory whether there's a packet ready for him, right? Like the receiver has to poll, basically.
And no, not at all.
Yep.
Sorry.
It's fine.
Oh, it's fine. Okay.
Can come up.
Okay, let's dig deep into the details. We use semaphores, for instance, to just do a push notification. Someone, the electrostatic sensor, for instance, is writing some new data. Then you can either try receive. You just say, is there any data or no data? Or you can do a blocking receive, and then you wait till you receive data.
How's that implemented?
With semaphores.
Okay.
Are there any further questions? So you can prepare the demo, maybe. Okay. I don't know. I'm gonna walk up. Who was that exactly? Can you pass it? Could you pass it? The microphone?
Of course.
Can you explain again what is the relationship between Cyclone and iceoryx? Is iceoryx a DDS implementation?
Mm-hmm. So basically, no, iceoryx is not a DDS implementation, but we're planning a partnership, and we just had the very first thoughts about how to combine the things, and we came up with a basic architecture, but yeah, that's currently in discussion. So iceoryx definitely is not DDS compliant. It's not a DDS middleware.
So do you support zero copy or almost zero copy communication between computers, between different computational units? like with RDMA?
Okay, we support zero copy only between in one VCU or one computer. If you have, for instance, communication between a multitude of computers which are connected, things, for instance, via TCP/IP, I think there are some concepts to do some kind of zero copy, but at the moment not. But if there are some concepts, I think it's feasible, and then we will try to do it.
Okay, cool. You've got the...
Yeah, the problem is he's not starting.
Okay, so we'll have to postpone that. So,
Sorry.
Sure. Are there further questions? So if you want to see it live, you can talk to us afterwards. Yeah, just here. Okay, just sure.
Have you looked at sealing? I looked into the code. I don't find if you were doing sealing.
Could you repeat sealing? What?
Yes, like MSD seal, basically right protecting the buffer after you transfer it to, or before you transfer it over to the receiver.
So basically, you should have a look at the SOFI implementation. This is our safely. Oh, okay, sure. The question was, how is this mechanism exactly working, if I understood it right, to do this atomic communication, so not how to seal the data, basically?
The buffer is right protected after it's sent over to the receiver. It can still be changed, right?
Repeat the question.
It cannot be changed. You can configure it that it can, but it makes no sense in our case. And we do this with ACLs, for instance. We have a shared memory separation with a multitude of segments. And then you have for the sender port a segment where he can only write data in it. And then you have a receiver port which can map this memory and only he can read it. And therefore we have separation of concern and have met our safety standard in this case.
Yeah, the sealing he was talking about is a feature of memory FPs in Linux, where you can write protect the buffer after you push it off to the receiver. So the receivers have a guarantee that the writer won't change the memory underneath that. Is there something like that?
Yeah, exactly. But the problem is we have to support QNX, and QNX does not support this.
Oh, yeah.
Okay.
Yeah, so we want to be POSIX compliant, or at least we're trying.
Yeah.
Thanks. Do you support overwriting data in case a consumer is not present? Imagine a producer needing to overwrite data repeatedly, and then the consumer connecting and consuming whatever data is available.
Okay, your question was if you are supporting overrating, and this means you are only interested in the newest data and not the old one from 5 years ago. And yes, we do this. It's our safely overflowing FIFO, which takes a lot of time to implement this thing, and yes, we do.
So you mentioned that you are aiming at safety quality, which will satisfy ACLD safety level, the highest safety level in ISO 26262. And my question is, are you going to provide some kind of a safety argument about your code, about your implementation, so that the users of your library could just plug it in and rely on whatever you have written?
Yeah, this is currently under discussion, so we really don't know really yet how things will work out there, but probably if you're interested, you can talk to us afterwards, yeah, sure.
Yeah, I think you're also here a newcomer. We are, I think, one of the first projects we are going open source and developing ACLD software open source. We have processes, but we have to gain experience how to handle this. For instance, you're a developer, have a crazy cool feature, we want to have it, you just make a pull request, and you say, yeah, it's cool, we don't want to have this in a car, then you have to fulfill the whole process to make it ACLD. And this contains a lot of reuse, requirements writing, and so on. And we have to figure out to realize this.
So also if you have suggestions or a similar project that was planning something like this, come talk to us, yeah?
Yeah, I'm swirling around here, just talk to me.
So, thank you very much. That's very interesting talk.